Welcome back, class, to the lecture that we started last week. As you remember, we're talking about single sample tests. So we're comparing a single sample to an overall population. Now just remember, when we say we're comparing a single sample to an overall population, what we're saying is that we've collected data on a single sample. Still remember that that sample represents a much larger population and that we're inferring from our sample to a population. So we're always comparing populations to each other, but for this particular test we will take a sample that represents one of those populations and we'll compare it to a known population. As you might remember from the online lectures last week, we had a scenario slide with Applebee's where we're implementing this new training program, and we took 30 new hires and we gave them this new training program, and we wanted to compare them to the performance of all employees in the organization. So we're going to take this new training program with our sample, compare it to the performance appraisals of all employees in the organization to see, or get an estimate to see if this new training program, if we were to implement it company-wide, would it be better than the current training that our employees are receiving. We introduced the steps for hypothesis testing, and in particular we covered the very first 3 steps. So we identified our populations, again performance appraisals of Applebee's employees with the new training compared with performance appraisals of Applebee's employees with the old training. We went through our assumptions as well and found that we met all of our assumptions for this particular scenario. Our dependent variable, in this case performance ratings, was scale. We did have a random sample selected from all new hires, so we met that assumption of random selection from the population. We also said it looks like we're meeting our normal distribution assumption because we have at least 30 employees in our sample. And then also we have the parameters in the population, in other words the performance appraisal ratings from the last performance appraisal given to all employees with the old training. We then stated our null and our research hypothesis. The null hypothesis being that there's no difference, and again the null means there's nothing going on. So we're saying that there's no difference in performance of our employees between the new and the old training. The research hypothesis is that there is a difference. So notice that we say there is a difference. Performance could increase, it could decrease. We're not really specifying here. We're just saying that performance might change. It could be higher, it could be lower, but that's our research hypothesis. We then talked about step number 3, identifying the measures of central tendency and variability for the test. All we're really saying here is that we need to know our mean and our standard error for the z-test that we're going to run. So we need to know the mean performance appraisal rating of the employees in the organization. So this would be with the old training. And if you remember from that context, we talked about having a mean of 72 with a standard deviation of 12. And so we need the standard error because we have a sample, so we need to get the standard error for a distribution of means. And if you remember, we did our calculations, and so the mean on a distribution of means stays the same as the mean on a distribution of scores. So in this case, in the population, the mean performance appraisal rating is still 72. We then calculated our standard error by taking the standard deviation and dividing by the square root of n. In this case was 30. So we took 12 and divided by the square root of 30, and we got a standard error of 2.19. So remember, because we're using a sample, we can reduce that variability by treating everyone as if they're the same in that sample, rather than treating them as if they're separate individuals. Some employees just naturally are going to perform better than other employees. We want to try to reduce that variability to get down to that average performance of the employees. And so our parameters in this case, once we took our mean and our standard deviation, we converted them to a distribution of means. We had a mean of 72 and a standard error of 2.19. Okay, so that catches us up. So that gets us through the first 3 steps. Let's continue on and let's do steps 4, 5, and 6, and then of course we'll talk about 7, the practical decision. So step number 4 is determining the critical values. So the critical values are that point on the distribution, the population distribution, where we're going to say that the mean of our sample is different enough from the mean of the population for us to say there's a true difference at a greater than chance level. So we'll set up a couple values on the distribution that if we exceed, then we are going to say we're going to reject the null hypothesis. So rejecting the null is rejecting that there's no difference. We're saying that it appears that there's support for maybe there's a difference with this new training program. When we determine the critical values on our normal distribution, we set up a region called the critical region where we will reject the null hypothesis. So when we say we reject the null hypothesis, we're saying again that we reject that there's no differences between our new training and our old training. So if we reject that there's no differences, then what we're saying is we find support that our new training is making a difference in performance. We call this critical value point alpha, or the P level. P stands for probability. It's the probability of incorrectly rejecting the null hypothesis. And what we mean by incorrectly rejecting the null, is that remember the normal distribution extends for infinity, that all values are possible. And so what we're looking for is those values that are unlikely to occur, or there's a low probability of occurring. So even though there's still a probability that it could occur, right, we're saying it's the probability so low that we can determine that there's a difference between the two training programs. But just remember, with statistics, there's always a chance that we're wrong. It's based on probability that regardless of our conclusions, there's always a chance that we're wrong. We want to keep that chance as small as possible, but there's always still that chance. And so that's what we mean by the probability of incorrectly rejecting the null hypothesis. The probability of being wrong if we say our two trainings differ from each other. So if we say we could be wrong, what we're talking about is what we call errors. And there's two types of errors that we'll be concerned about in this class. They're what we call type 1 and type 2 errors. Now errors can come from several different sources. Sometimes they're the result of chance, just chance variation in the population. Sometimes they're because we conveniently sample from the population and we don't randomly sample. And sometimes it's due to poor methodology or poor research design. Now, the errors that we're going to be concerned about with z-test and just probability testing in general are errors due to chance. What we mean by errors due to chance means that it could be possible that the sample that we get, so remember in this example we randomly sampled 30 new hires, it's entirely possible that when we randomly sample from our population of new hires, that we could get just by chance 30 new hire employees who just happen to be high performers. So it has nothing to do with the training they received. This new training is just because they work really hard and we just happen to get 30 of them all together. Now the chances of us getting 30 high performers randomly is really, really low, and so it's not likely to occur, but there's still that probability, and that's what we mean by errors due to chance. So there are two types of errors that we'll talk about in this class. The first one is what we call a type 1 error. This is a false positive. So this is where we say we reject the null hypothesis in our study when the null hypothesis was actually true in the population. So what we mean by that is that we might say there's a difference between our training programs, the new and the old training program, but in reality there is not. It just so happened that we randomly selected 30 high-performing, recently hired employees, and the training did absolutely nothing. Their characteristics already they were high performers, they're hard workers, and the performance ratings that we get is because that is their personality and it has nothing to do with the training that we gave them. So that would be an error. That would be saying that training worked when in reality it didn't. We just happened to select a bunch of hard workers. That's a type 1 error, that's a false positive. Another way to think about it is if you were to go to see the doctor and the doctor told you had cancer and in reality you did not. The problem with type 1 errors is that they typically result in unnecessary action. So if you think about it, if you went to the doctor and found out you had cancer, you'd probably be pretty upset, but more importantly, you'd probably go through a lot of painful treatment to take care of a cancer that is not there. And so in that sense, we waste a lot of resources. And so when we have a type 1 error, that type 1 error typically results in unnecessary action. We say something's going on, but in reality, there is nothing going on. Nothing is happening. In contrast, we have the type 2 error, so this would be a false negative. This is where we failed to reject the null hypothesis. So in other words, we failed to reject that there's no difference, when in fact the null was false. So this is like saying there is no difference in training programs when there is actually a difference. So for whatever reason, maybe we randomly sample from our new hires that receive this new training, and it so happens that we, just by chance, sample 30 really poor performers. So in this particular case, we don't find a difference between the new and the old training program, not because there wasn't a difference there. Maybe the training program is effective, but that training program effectiveness was canceled out by the fact that we sampled a bunch of low performers. So we say there's no difference in training programs, but in actuality there is, and so that's an error. This is like going to the doctor and being told that you don't have cancer when in actuality you do have cancer. Now, type 2 errors typically result in no action. And if you think about it in the terms of cancer, if you find out that you don't have cancer, then you continue with your daily activities that you normally would do. Maybe you continue smoking, maybe you continue going to the tanning booth, maybe you continue to change your oil by hand without using any type of gloves or anything like that. And those are all carcinogens, and so you don't change your behavior, and you certainly don't get any kind of treatment. Sometimes it's easier to put our errors into a contingency table. So here's a 2x2 contingency table, and if you look at the very top row, we have two particular decisions. We should reject the null hypothesis in the population, or we should fail to reject the null hypothesis in the population. So remember, the population is something that's not usually directly available to us. Usually the population is so large that we actually don't know what's happening in the population. So even though the population is inaccessible to us, the sample is accessible to us. And so based on our sample, we may make a decision, or in other words, based on our research, make a decision either to reject the null or to fail to reject the null hypothesis. Now, based on our research study, based on the sample, if we reject the null hypothesis, and in the population we should have rejected the null hypothesis, then we would have made a correct decision. In this case, our decision based on the sample we collected matches that in the population. Now let's say based on our sample that we reject the null hypothesis, but in reality we should have failed to reject the null hypothesis. Then we have made an error. In fact, we have made a type 1 error. So with a type 1 error, we say there is a difference, but in reality there is not a difference in the population. And again, this happens because we're sampling from the population, where the population isn't directly accessible to us. We don't know what's really happening in the population. We just base it on the sample. And so if we make an error in saying there's a difference when there isn't, then we've conducted a type 1 error. So if based on our sample we decide to fail to reject the null hypothesis based on our statistics in the sample, and in the population we should have rejected the null hypothesis, so in other words we say there's no difference but in reality there is a difference, then we made another type of error. We made a type 2 error. So again, a type 2 error is where we say there's no difference when in reality there is a difference, and just because of chance, just because we happen to sample a group of people that didn't reflect that population, or maybe scored low or high, it canceled out the effect that really would have been there had we had a representative sample. Alright, and so then that leaves the last box here. Again, here with our sample we decide to fail to reject the null based on our statistics, and in reality we should have failed to reject the null hypothesis in the population. If that occurs, then we've made again a correct decision. So like I mentioned before, students sometimes find it helpful to see it in a table all in one spot. I hope it helps you as well. But just make sure you know the difference between a type 1 and a type 2 error and how it relates to hypothesis testing in our statistical decisions with hypothesis testing. So getting back to critical values, so the alpha represents that critical value or that point where we're going to reject the null hypothesis. But remember, with statistics there's always a chance that we're wrong. So alpha also represents the probability of incorrectly rejecting the null hypothesis. So saying that there's a difference between our groups when in reality there is no difference between our groups. So the researcher decides the alpha, or decides the risk they're willing to take in saying there's a difference that may not be there. So by convention, an alpha of 0.05 has been accepted by the publishing community when it comes to the behavioral sciences. So an alpha of 0.05 being a probability, if we turn that into a percent, so we multiply it by 100, it's a 5% chance of being wrong. In particular, a 5% chance of being wrong by saying that there's a difference between our groups when there really isn't a difference between our groups. Now we can be more strict with alpha, so we can set an alpha, let's say 0.01, which would be a 1% chance of being wrong, or we can even be more strict than that. It's up to the researcher to decide. We could be more liberal as well and say an alpha of 0.20, but if we were to do that, we'd have to have a really, really good explanation as to why a 20% chance for an error would be appropriate. And there are those circumstances where it might be appropriate. So when we talk about alphas and setting up critical values, we need to talk about directionality. So do we expect values to increase, decrease, or are we not sure what's going on? And so that's what we mean by directionality. So there's three types of alphas that we're concerned with when it comes to hypothesis testing. There's the extreme alpha above the mean, or in other words, an extreme alpha higher than the mean. And this is when we have a situation where we expect values of our measure to increase based on our sample to the population. There's also extreme alpha below the mean. This is lower than the mean, so this is where we would expect values that we measure for our sample to be lower than the mean of the population. And then there's the extreme alpha above or below the mean. In this particular case, we actually don't know what to expect. Values could increase, they could decrease, we don't know, and because we don't know, we need to set our alpha in both tails. Now when we set our alpha in both tails, we have to divide that alpha by 2. Essentially making a harder test or a stricter test, making it harder for us to reject the null hypothesis. And the reason we do that is because we have to pay a penalty for not knowing what to expect. That based on theory, we should have a good idea of whether or not our value should increase or decrease. And if we don't know, then we need to pay a penalty, and we make a more conservative test or more strict test, and we divide our alpha by 2 and look in both below and above the mean. So let's go ahead and let's take our scenario and let's reword it slightly to reflect an alpha above the mean. And so in this particular case, let's say we have alpha b's again, so everything about the scenario is the same except we changed a few words, and so maybe they have implemented a validated and new training program that has been shown to increase performance. What we mean by validated is that this particular training program has been researched many times with very different populations and have been found to increase performance. So in other words, we're implementing a program that has worked in other organizations. There's no reason to think it won't work in ours. And if that's the case, then we can set our alpha above the mean. We can expect that performance is only going to increase, and so we can ignore the fact that performance might decrease. We're only looking in one direction of our distribution. So we can represent this visually. So here you have a normal distribution. This is a normal distribution in the population of means, so distribution of means. And as you remember, the population distribution extends for infinity in both directions. So negative infinity to positive infinity. So that means all values of z are possible. Now, the more extreme you get, or the more different you get from a mean of 0 or a z-score of 0, the less likely it is to occur. Remember, the y-axis here is frequency. So the less likely it is to occur, the less the probability is. So at some point on this distribution, we can say that there is a low chance of our conclusion happening by chance. And so that's where we're setting our critical region. So in this particular example, we're going to set our alpha at 0.05, so convention, a 5% chance for an error. And if you look up on your z-statistic table, remember this is table B1, and you look up 5% in the tail, you will get a z-score, or a z-statistic in this case, a z-statistic of 1.65. So that z-statistic is the cutoff point, that critical value, where if we get a z-statistic greater than 1.65, then we will say we will reject the null hypothesis. So we set up our critical region at a z-statistic of 1.65. That represents 5% of the distribution in the tail, or 5% of extreme values for z-statistics. If our z-statistic for our test, our hypothesis test for our research study, is greater than 1.65, then we will reject the null hypothesis. Now remember that statistics is based in probability, so there's always a chance that we're wrong. So this population distribution in our particular context would represent the old training program. And so on that old training program, we would expect that 5% of the population of employees would have a z-statistic greater than 1.65 when they're in groups of 30. And so that means that if we get a z-statistic greater than 1.65, it could be because of our new training, or it could be because of chance. Now, because that z-statistic is greater than 1.65, we're going to say it's likely due to our training and not due to chance. But just remember that any z-statistic is possible when we take our z-statistic and we compare it to chance, or compare it to our table in B1. It gives us a chance, or a percent for a type 1 error. So here, alpha is 0.05. We're saying there's a 5% chance that if we say our training program works, when we exceed that value of 1.65, that there's a 5% chance that we could be wrong. But likely, any difference would be due to the training if we exceed that z-statistic value of 1.65. Now remember that the alpha is decided by the researcher, so we could just as well assume a 10% chance of being wrong. And so maybe we decide to use an alpha of 0.10. And so if we look on our table on B1, we look at 10% in the tail, we'll see that an alpha of 0.10 is equivalent to a z-statistic of 1.28. So note that the z-statistic is now lower, it's closer to the mean. So in other words, it's easier to reject the null hypothesis, that it doesn't take as much of a difference between the mean of our sample and the mean of the population for us to say that there is a difference. But that also comes with a higher increase for an error. And so now our error rate, our type 1 error rate, would now be 10% instead of 5%. So if we do reject the null hypothesis, there's still a 10% chance that we could be wrong. And again, that's because we would expect 10% of the population with the old training to score higher than a z-statistic of 1.28. Okay, so what if we had an extreme alpha below the mean? So here might be a scenario where we would expect this new training program to result in decreased performance. And so again, based on research, we may find that a particular program that we're implementing is going to decrease performance. But maybe that decrease in performance is more cost effective. And this does happen with organizations from time to time. I know when I was a store manager, I saw our training hours drop from 8 hours to 4 hours to 2 hours to no hours, because they found it was more cost effective for employees to learn on the job than it was to spend that extra money and time to train them. And so sometimes organizations will implement new training programs that actually decrease performance, especially in the short term, but in the long run it's more cost effective. If that's the case, then we can visually represent it again with our distribution, except now note that we're now looking in the negative direction and the negative direction of our distribution. So we would expect performance to be less with our sample than in the population, and that would give us a negative z-statistic. And so here, let's say we have an alpha of 0.05. So again, there's 5% of our population of the old training that would get a z-statistic that is negative 1.65 or more extreme. And so we can set that cutoff point at negative 1.65. If our sample was less than negative 1.65, so let's say negative 2, then we would reject the null hypothesis that there's no difference. It would appear that performance had decreased at a greater than chance level. Again, remember that when we reject a null, there's a certain level of probability that we're wrong. If our alpha is 0.05, then we're saying there's still a 5% chance that we could be wrong if we say performance has decreased relative to the overall population. So now again, the researcher gets to decide what alpha is, and so maybe the researcher decides, or we decide, that alpha should be 0.10. In other words, a 10% chance of being wrong. And so we can take a look at our distribution here, and we see it's in the negative direction, so we'll set that region up in the negative direction. If we look at our B1 table, the z-statistics table, and we look up 10% in the tail of the distribution, we will see that there is a z-statistic of 1.28. And again, because we expect performance to decrease here, we would make it a negative 1.28. We expect the values to be lower for our sample than from the population. So the last type of alpha that we'll talk about is the extreme alpha above or below the mean. In this particular case, what we're saying is that we don't know what to expect with our training program. Maybe the performance will increase because of the training program. Maybe it will decrease. We don't know because it's never been tested. Maybe we developed this training program itself. So whenever that happens, we have to take our alpha and we have to divide by 2 to account for both directions of our distribution. So this would be the example that we started off with this Applebee's context. In particular, we want to know the success of the program, but we don't know if it's going to be successful or if it's not going to be successful. It might increase performance, it might decrease performance. We actually don't know, and we don't have any research to suggest either way. And so when that occurs, then we have to look in both tails of our distribution and not just one of the two tails. So we can visually approximate that type of scenario by drawing out our distribution and setting up our alphas in the two tails. So remember, if we set our alpha at 0.05, that we have to divide by 2 to account for the fact that we're looking in both tails. So we divide by 2, our alpha 0.05 divided by 2, and we get an alpha of 0.025 in each tail. And so we can set up critical regions based on those two alphas, that if we get z-statistics greater than 1.96 or less than 1.96, and again, look at your B1 table to get those z-statistic values, then we would reject the null hypothesis and say that there appears to be a difference with our training program. Now, the key thing to remember here again is that we're dividing by 2. Note that it becomes harder to reject the null hypothesis. That even though we set our alpha at 0.05 overall, we're only looking at 2.5% in each tail, and that makes it harder to reject the null hypothesis. It also makes it less likely that we get our results by chance, and that's a good thing as well. So again, alphas can be set by the researcher, and so this might be an example of an alpha of 0.10. We divide by 2, we get 5% in each of the tails of the distribution, and that gives us z-scores of negative 1.65 and z-score of 1.65, again because we're looking in both tails. So how we set up our alphas relates back to the null and the research hypotheses. That depending on the type of alpha we have, that changes our null and our research hypothesis statements. And so you need to know how each type of alpha affects or changes the null and research hypothesis that you will need to write when it comes to a study. So when we have an alpha, extreme alpha above the mean in the population, then what we're saying is that we expect that performances based on our sample will be higher than the mean. And so that changes our null and our research hypothesis statement. It is usually easier to start with the research hypothesis when you have a one-tailed test. So here we expect performance to increase. So we might say performance of Applebee's employees is higher with the new training program than with the old training program. We expect that performance is going to be higher, so we'll look in the positive direction of our distribution. We won't be concerned about the negative direction. And if that's the case, then we will say performance will be higher with the new training than the old training program. Now note that we still have all of our components of a hypothesis test here. We still have a different statement. In this case we're saying higher. We're still saying who's being measured, Applebee's employees. We're still saying the measurement performance, and we're talking about our two groups, new training program with the old training program. So what's important with the null hypothesis now is that we have to account for all parts of the distribution. And so we can't just say the null is that performance will be lower, but we have to say that the null is that performance will be lower or equal. So in this case we might say performance of Applebee's employees is lower or the same with the new training program than with the old training program. So we can't just say lower, we have to say lower or equal, because either one of those would designate that our training program is not having the desired effect. So the research hypothesis is performance will be higher. The null is that it will be lower or equal. Now let's say we expect performance to decrease. So again, we might implement a training program that decreases performance, but in the long run increases profits. And so in this particular case, we'll set up our distribution in the negative direction. We expect performance to decrease. So that means our research hypothesis will say that performance will decrease. The null will be that it stays the same or it increases. Again, it's easier to start with the research hypothesis if you have a one-tailed test. In other words, you're looking in only one tail of the distribution. And so here we would say that performance of Applebee employees is lower with the new training program than with the old training program. Once we have the research hypothesis, it's then easier to go back and do the null hypothesis. So if we expect that performance will decrease based on the research hypothesis, then our null hypothesis is going to be that we expect performance of Applebee's employees to be higher or equal with the new training program than with the old training program. So again, we have to count for the entire distribution, not only where it's higher and lower, but also in the middle where it's equal. And so the null will be higher or equal with the new training program. Then finally, what if we don't know what to expect? Performance could increase or it could decrease. We're not sure. And so we'll set up our distribution to look in both tails. We'll set up critical regions in both tails of our distribution. And in this case, our null hypothesis is that there's no difference in performance. In other words, the middle part of our distribution, there's no difference between the new and the old training programs. The research hypothesis is that there is a difference. Now again, we don't specify whether it's going to increase or decrease. We're just going to say there is a difference. Maybe it increases. Maybe it decreases, but now we account for our entire distribution, the middle part where there's no difference, and the two extremes where there are differences, where performance could increase or it could decrease.